Okay, let's start. So, hello everyone, my name is Rijoy Mukherjee and I am a research scholar at Department of Computer Science Engineering, IIT Kharagpur. So, I will be conducting this live session for the NPTEL course on computer organization and architecture. So, we'll be solving some questions and sample questions, and the session will be interactive. So, feel free to ask any question like in the chat whenever you have any doubt. So this session is being recorded so that everyone can view it after the session is over. Can everyone hear me? Yes, this is the first class. So there will be around 12 or such sessions. So okay, let's start. So this is one question. So this is a very sample question. This is a very easy MCQ question. So as to just start the session. So the question is, which of the following is or are false? So you can write the answer on the chat. Let's see how many can do it. Anyone? Okay, so the question is, which of the following is or are false? So the first statement is processor can directly access data from the secondary memory. So this question is, this statement is false. So we know the processor, yes, it is A, B, and D. Yes. So let me discuss it. So option A is the processor can directly access data from secondary memory. So this is false because processor can only CPU can only access data from a main memory, not the secondary memory. The number B statement is also false because primary memory is not used as backup memory. It is secondary memory, which is basically used as backup memory. Number C. So if you notice, statement number C and D are little bit contradictory. Like number C says primary memory stores the active instruction and data for the program being executed on the processor. So, and the statement D says the primary memory can only store instructions. So that is not correct. Primary memory stores both instruction and the data of the program that is on the processor. So statement C is true, whereas the statement D is false because primary memory stores both instruction as well as the corresponding data. So it is option A, B, and D. Any doubt? Okay, I will go to the next question then. So question 2 is, which of the following is or are false? So you can try, you can write the answer on the chat. I will see how many can do it. Yeah, Rahul is correct. Nidhi is also correct. Yeah, everybody has got it. Yeah, so these are very basic questions, but it is good to review the concepts which you have learned in the first lectures. So CPU we know consists of only control unit plus ALU, and number B statement says there are two types of memory. It is correct. Number C statement says arithmetic and logical operations are performed in the control unit. So this is false. It is basically ALU. It is basically the ALU which does these operations. And number D is the control unit is basically is a part of main memory. No, control unit is part of CPU. Yes, this session is being recorded, so you will get it afterwards on I guess YouTube. The link will be shared with you. Okay, so let's move to the next question. So the question is, for a 512 cross 32 bit memory that contains 512 locations each with 32 bit data, which will be the address of the 389th location, assuming the first location is 0. So basically it says that you have a chunk of memory there are total 512 memory locations. Each location has a 32 bit data. So if the address of the first bit is at 0, so what will be the address in 389th location? Question is simple. So anybody wants to try? Okay, take 1-2 minutes, that's not an issue. You can try, like, it is good if you try also along with me. I will solve it. Yeah, one have given the correct answer. Okay, okay, I'm solving. Okay, so this address bit has a this first memory bit is at location 0. So consider as is a simple array. So in a simple array like which we have done in data structures, so the memory is stored in a contiguous location. So it will be at 0th location, 1th location, 2 location, dot dot dot. So here it is being said that if the first item is at 0th location, then what is the at what location 389 is stored. So basically 389 will be stored if the 389th location will be basically at the 388th array position. So, you must be wondering why, then what to do with the 32 bit. So 32 bit is the data that will be stored in these locations, but the address will be linearly because here it is not mentioned like what is the size of the address. So basically each, so first one will be 0, second one will be 1, second one will be 2, so, and the last bit will be 511. So the binary value of 388 will be the answer. So if you do it, it will be 1 1 0 0 0 1 0. That is option A. Yeah, so if you have any doubt, you can ask me. I will do it again. Yeah, it is option A. Yeah, so as you can see, the bit memory. So basically you can consider a bit memory basically a RAM or some kind of an, what is a RAM? RAM is basically a contiguous location. You can consider it as a contiguous location of an array. So, so if the first bit address is 0, so the that means the 512 will be, the last address will be 511. So, so so the address locations are basically 0 to 511. Now here it is said that what will be the address of 389th location. So the 389th location, so first if the 0, if the first address is if the first address is 0, second address is 1, then 389th will be 388. So now the binary value we have to find of 388. Now it's clear. Okay, how to find binary value? Okay. Uh, so how to find binary value of 388? Okay, let's do it for a smaller number. 388 is a very big number. Suppose 55. So if we divide it by 2, so if we divide it by 2, so it will be 20. 27, the reminder and the quotient, and the remainder will be 1. So next, if we do it, it will be 13, and remainder will be 1. So again we will divide it by 2, so it will be, quotient will be 6, remainder will be 1. Again divided by 2, quotient will be 3, remainder will be 1. No, sorry, remainder will be 0. So again if we do it, so quotient will be 1, remainder will be 1. So this is the binary value, 55. No, it is not 388 into 2. 388, 388. So the 32 is basically the size of the address that is being stored. So you don't have to consider that. Okay, so let's move to the next problem. So it is being said that there are two registers that are initialized as R1 is equal to 30 and R2 is equal to 25. Two registers are initialized, R1 is equal to 30 and R2 is equal to 25. So the instruction add R1 R2 is in the memory location 2018H. So this is an hexadecimal number 2018. So if the size of the instruction is 4 byte, then after the execution of the instruction, the value of PC R1 and R2 will be which one? So I will solve it. So if it is 588 cross 16, so then it will be so what is 588? 588 will be the last address. So it is the size of 588. So so the last, so it will start from again 0, 1, 2, dot dot dot, and the last one will be 587. So the answer will be same. It will always be. So if the question was to find the address of 389th bit, so it will always be the one less in that case. So this one, okay, so let's do it. So So it is so it is being said, so add R1 R2. So consider this to be the memory. So consider this to be the main memory. So these are address locations in the main memory. So it is said that the instruction is in the memory location 2018. So it is in, suppose, this location. So this is 2018. So, and it is said that the size of this instruction is 4 byte. Okay, so size of this instruction is 4 byte. Now also it is being, so what is this asked? The ask is what will be the value of PC R1 and R2 after the execution of the instructions. So what is PC? PC is program counter. So what does program counter do? Program counter stores the address that will be executed next. So currently program counters holds this address. So that is, program counter holds this address where it will be fetched from. So that is 218. So PC is currently 2018. Now when the program gets executed or is being executed, the value of the PC is incremented and is pointed to the next instruction that will be executed. So what will be the next instruction that will be executed? That will be this one. So this one is 2018. This one will be the next instruction that will be executed. So what will be the value of PC after execution? So after execution, PC will become PC plus 4. Why 4? Because size of the instruction is 4 byte. So that is 2018 plus 4. That is 201C. Now what will be the value of R1 and R2? So this is a 2 address instruction. So in 2 address, what happens? So this will be the underlying instruction that is being executed. R1 is equals to R1 plus R2, that is 30 plus 25, that is 55, and R2 will be remain same because the operation is done on R1. So R2 will be 25. So the answer is D. So if you have any question, you can ask. So how will R2 remain 25? See the this is a two okay, so all our question same. Okay, so this is a so the instruction is add R1 R2. So this is a two address code instruction. So in two address code instruction, uh, this is what happens basically in two address code instructions. So here the operand are R1 and R2 and it gets added. The instruction is add, so add is being occurring. So and the value is gets stored in R1. See, the value does not change of R2, that's why, because the value ultimately the value of R1 is only getting changed as a reason. Yeah, so 2018 plus 4 is 2016, sir. Yeah, so so you need to see that this 2018 is a hexadecimal number. So if you add 4 to it, so what is so how what are the hexadecimal numbers? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So if we add 4 to 8, so it will be 1, 2, 3, 4. So that's why it will be C. Okay, so clear now? Okay. So let's go to the next question. So here the question is, consider a 32-bit machine where an instruction add R1 R2 is stored at memory location 2004H. So what will be the value of IR and PC when the instruction is fetched and executed? Consider the individual instruction is 32-bit. So what is so let me just draw some figures so that it will help you. So add R1 R2, this is the memory. So again it is said that it is stored at location, suppose this, and the location value is $2004. So what will be the value of IR and PC when the instruction is fetched and executed? So IR is basically instruction register. And PC is program counter. So all the instructions are 32-bit, so we don't have to think about it now. So so what is instruction register? And our last question we discussed what is program counter. So basically when so presently this instruction is stored in this location. So when this instruction, so how does CPU? So the CPU has to conduct this operation, that is addition of registers R1 and R2. So for that reason, you need to bring the data. So this instruction from the memory to itself. Now the CPU does not have any memory to itself. It has the registers. So when this instruction, this add instruction is fetched, it gets stored, it has to be stored into this instruction register. There are many functions of this instruction register. This instruction register decodes what instruction that is inside it. Like it can be an add operation, it could be an OR operation, it could be a subtraction operation, it could be a multiplication operation. And as we showed in the last question, what is program counter? Program counter is basically the like now currently this instruction is being executed. So after it will point to the next instruction that will be executed after this. So it will always point to the next instruction that in line that will be executed. So so in the lectures of this week, you have been introduced to two terms, two kinds of registers: MAR, MDR. So what is MAR? MAR is memory address registers, which basically points to address location, and memory data location, data registers, it basically stores the value of MAR that is stored in MAR. So MAR stores the address and MDR stores the data that is stored in that address. So this instruction, so this all you have been introduced in this week's lecture. So this operation starts like this. So initially PC will be stored in MAR. So what is PC? PC is at this present it is basically this value, that is MAR equal to 2004. Now the next operation is program counter value. Program counter points to the next instruction that will be executed. So PC is equal to PC plus 4. Why 4? Because it is 32-bit, so basically 4 byte. So PC will be 2004 plus 4 2008. Next, MDR. What does MDR store? MDR stores the data that is stored of the address that is stored in MAR. So that is basically mem MAR. Now what is the value of MAR? MAR currently contains 2004, and what is stored in 2004? This address. So basically, like this instruction, sorry. So basically MDR will store now add R1 R2. Next, instruction register stores what that is stored in MDR. That means IR will contain add R1 R2. So this is the value of program counter, and this is the value of IR. So the correct answer is option C. Sir, if we are, but if we are putting R the value of, if we are putting the value of R2 and R1, then how it will remain? Yeah, so if you look at this, the we are not putting the value of R2 in anywhere. It is not that just not a dustbin that you will just empty it after it. The value will remain there. It will be remain there. So R1, what was the value previously? R1, the value was previously 30. It is being overwritten here. R2 value will remain same. It is the R1 where the value of R1 plus R2 is getting stored. Okay. Why 4 added, sir? Why did always? Okay, so see the individual instruction, it is clearly said 4 bit. So what is 4 bit? 4 byte. 32 bit, sorry, 32 bit it is written, the individual instruction is 32 bit. So that means this is 32 bit size. So 32 bit is basically 4 byte. So that's why, so if this instruction begins at 2004, so the next instruction starting will be 2004 plus 4, that will be 2008. Okay, so okay, I will explain it once again. These are it. So basically we have an instruction add R1 R2. So it is said that R1 and R2 is located at memory location 2004. So this is the main memory, and it is being and this is the location where this instruction is stored. So next, what is IR? IR is instruction register. So basically, what is instruction register? Instruction register stores this kind of statement data. This is the kind of data that is being stored here. The speciality of instruction register, it does much more thing. You will be accustomed to it in the future lectures in future weeks. So IR basically stores the instruction register, and PC stores the program counter. So program counter stores the address from where the next instruction will be executed. So currently the PC value is 2004. So when this is being executed, it will point to the next instruction. So that is 2008. Next, I talked about two more registers, that is MAR and MDR. What is MAR? MAR is basically memory address register, and MDR is memory data register. What does MAR do? MAR stores one of these addresses. Like in our case, it can store 2004. What does MDR do? MDR stores, so you can see the thing here, MDR basically stores the data that is stored in this memory location, that is the location, that is the address that is currently stored in MAR. So MAR currently is 2004. What is inside 2004? This instruction, this add instruction. So MDR, this instruction will be fetched and it will be stored in MDR. And so this is the process of execution. This is a standard process of execution. It has been introduced in the week 1 lectures I have seen. So MAR first stores the PC. PC gets incremented by 4 because that is where the next instruction will be stored. Then we store the fetch the data of MAR inside MAR, and we store it inside MDR. Next, the MDR transfers the data into IR. So what does MDR had? MDR has had this instruction, and so IR will contain this instruction. Okay. Okay, let's go to the next problem. So this says, so for a byte addressable computer which has 4 GB of memory, if each word in the computer is for 64 bit, then how many bits are needed to address a single word? So there are many terms here. Many of you may know and many doesn't know. So first it is said that the computer is byte addressable and it has a memory of 4 GB. Next, each word is 64 bit. Of this computer is 64 bit. So what is a word? Word is basically a byte or multiple of byte. So in this case, also what is the total memory? So here total memory is 4 GB. And it is also said each word is 64 bit. So one word (64 bit), which is basically 8 byte. Now we need to find how many bits are required to address a single word. To address a single word, how many bits are required? So first we need to find out how many words are there total. So this is the total memory. This is the size of one word. So therefore total number of word equal to, so this we can write as 4 GB is basically 4 GB divided by 8 bit. So what is 4 GB? 4 GB is equals to 4 into 2 to the power 30 B, and it is 8p. That means total number of words that we have is 2 to the power 29, right? So this is the total number of words that we have. So how many bits are required to address a single word? That means, so let me again draw a structure. This is total 4 GB. Here each one is 64 bit. So therefore there are total 229, 2 to the power 29 such locations in this memory. Therefore to address each memory we need 29 bits. That is option A. Yeah, one word is not always 8 bit. In this question, it is 1 bit. because here it is written that if each word is 64 bit, so 64 bit is 8 byte. Okay, I will repeat again, I will do it once more. So first consider this is the memory. Suppose the total memory is said that it is 4 GB, and each word is 64 bit. So we need to find, so our ultimate target is to find how many bits are needed to address a single word. So how many bits are needed to address this single one. So there are 4 GB memory, and each word is of size 64 bit. So total memory is 4 GB, one word is 8 byte. So therefore first we find the total number of word. So total number of word, if we calculate, it comes down to 2 to the power of 29. Now, so therefore it means there are 2 to the power 29 such locations here. There are 2 to the power 29 such locations. Now to address each location, we need then 29 2 to the power 29 bits. Okay, let me check. Okay, you can on the mic. Rohit, you can ask.
Hello.
Yeah, ask.
Sir, I want to say that here you write that one word is equal to 64 bit, and
Yes.
when we are using here, sir, we are using 4 GB and by 8 byte. Sir, here B stand for byte. That's why I want to say, sir, as we can use here 64 bit, or sir, here B stand for byte, and here GB when we convert it is bit. So,
So no, no, no.
then sir,
GB is also byte. It's not bit.
it, it is byte, sir.
Yes.
Okay, sir. Then my doubt is clear, sir. Thank
Yeah,
you.
it is byte. So see, whenever we write capital B, it is always byte, and small b is bit.
Okay, sir. Actually, I think that here is it is bit. That's why I have
No, no, no.
doubt.
It is
Now my
byte.
doubt is clear. Okay, sir. Thank you.
Okay. 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 So, so let's go to the next question. So this is a little different kind of question. So, so it is given if the numerical value of a 2 byte unsigned integer on a little Indian computer is 255 more than that on a big Indian computer, which of the following represents the unsigned integer of a little Indian computer? Okay, it is little difficult, I understand, but I will explain it. Okay, so it is said we have a suppose suppose a number a. So suppose suppose what I saw little Indian and big Indian was taught, so I include this question. So suppose a has a value 0 0x 0 1 2 3 4 5 6 7. Now let's so little in what is little Indian and big Indian? So little Indian and big Indian are basically ways to store a byte array, multiple byte array. So it can be an int, it can be a float. So in Little Indian, it is basically stored like this. So Little Indian 6, 7, 4, 5, 2, 3, 0 and 1. So suppose this is the 0th bit, first bit, second bit and third bit. So Little Indian, so this is the lower address. So lower address always stores the lower byte. So this is the lower byte 6, 7 store first byte stores 6, 7, then 4, 5, 2, 3, 0, 1. Now in Big Indian, the opposite happens. So 0, 1, 2, 3, 4, 5, 6, 7. So here the lower bit stores the lower address. Lower bit is stored in the lower address. So this is how the two types of data storage way, Little Indian and Big Indian. So in the question it is said, so in out of all these 4 options, which of the following has a difference of 225 when it is basically stored in a Little Indian format and that of a Big Indian format. So basically, suppose suppose it is x little minus x big is equal to 55. So you need to find this one. So which of these, like x are basically like suppose A, B, C, D. So which of the following have a difference of this? So let me show how it is done. So basically 6, 6, 6, 5. So for option A, suppose it is A. For option A, 6, 6, 6, 5 minus 6, 5, 6, 6. So this is Little Indian format and this is Big Indian format. So what is the difference between this? It will be FF. See, the difference between this and this is basically 255. These are hexadecimal numbers, and if we do the number B, so it is basically 0x1 sorry, basically 0, 0, 0, 1 minus 0, 1, 0, 0. You see, this is a negative. This number is smaller than this, so it will not be 255. So we can just omit it. This value will be different. So similarly, if we do C also, you see the lower bit is smaller than the upper bit. So it will also be it will also be a negative number. Whereas D, it is again same. The smaller bit is greater than the like the smaller bit is greater than the upper bit. Lower bit is greater than the upper bit. So the answer will be A and D. So the total number of words is 299. Yeah, so okay, 1 minute. Yeah, so you see the total number of words is 299. The question is how many bits are needed to address a single word. So mm, suppose how many words are here? One, two, three, four, right? So how many bits will be required mm, uh, to do this? 2 bits, right? One, two, three, four. So 2 to the power 2 is equal to 4. So this is a small example like how it has to be done. Any question on this one? Question 7. How you how so how 6665 convert to into 56566? It is not understand. Okay, 1 minute. So you understood what is Little Indian and Big Indian, right? So let me clear the frame. So this is 6665. This is Little Indian. So the Big Indian form will be 6566. Look, this one goes here. This byte comes here. This byte comes here. So let me explain it much better. So in Little Indian, lower bytes contain the lower address. So this is Little Indian and this is the Big Indian. So basically, you just swap the data. So in case it is 1, 2, 3, 4, 5, 6 in Little, it will be 5, 6, 3, 4, 1, 2. So if it is 1, 2, 3, 4, 5, 6, 7, 8. So it will become 7, 8, 5, 6, 3, 4, and 1, 2. So this is Little Indian and this is Big Indian. So the question was, which of the following will have a difference of 255? So if you see 6665, that is Little Indian, and the Big Indian is basically 6, 5, 6, 6. If you do a difference, these are hexadecimal that you need to remember. So basically it will be F, the difference between 6 and 15. If you check, it will be F and the carry will be here. The difference between 6 and 15, so basically 5 is here. If we borrow 1, So it will be 15. That is total 16 difference. So it will be F. So again the carry will be here. It will again be F. So this will be the your difference. So if you calculate, A will give a difference of 255 and D will also give a difference of 255. But if you check B and C, so if you check B 0 0 0 1 0 1 0 0, you see this value is greater than this. So basically it will not have a value of 255, it will be a negative number. Okay. So that was the last question. You can ask any question regarding this session if you want. If you have any question, you can ask, then else I will stop the session. Question 4. Question. Yeah. So every Tuesday there will be problems. Yes, it will be there for every Tuesday, 6 to 7. So Ashish, what is your like question for what is the doubt? Data entry. Okay, I'm giving you the mic, you can ask. Ashish, you can ask. I've given you the mic, you can unmute yourself and ask.
Hello.
Yeah, Ashish.
Sir, actually, my question was, sir, if you are putting our data of sir our register 2 in register 1, then sir, how the register 2 will be empty only?
No. We are not putting the value of register 2 in register 1. So basically what we are doing, we are summing of R1 and R2. So that is 30 plus 25. And we are putting that result in R1. We are not touching the value of R2. R2 is R2. R2 will be stored there. We are not deleting that value.
Oh. Sir, that data will be only there.
Yes, that will be there. It will not. It is not being stored there. So load and store concept, like until and unless something the value of R2 will remain 25, unless and until some other instruction stores some value in that R2.
Thank you, sir.
Okay.
Yes, sir. Thank you, sir.
Okay. Faizan, what is your question number 7 doubt? Week, Rohit, week 0 question number week 0 question number 6. I don't have it right now. You can mail me, okay? Right? You can write in the forum. I can explain that. I don't have the question with me right now. Faizan, what is the, why should we put value? Put the value 1, 2, 3, 4, 5, 6. No, I was just explaining it. Okay, let me do it once. So basically, see, this is a Little Indian way of representation, this one. So what happens in Little Indian, the lower value, lower bit stores the lower byte stores the lower address stores the lower byte. So this is the lower byte, and the lower address stores it. So basically, it is 0, 1, 2, 3. So this is the lower byte, and this is the lower address. So lower address stores the lower byte. Whereas in big Indian, the lower byte stores the upper, lower byte stores the upper, lower address stores the upper byte. So this is the upper byte, right? So this upper byte is stored in the lower address, that is 0, and vice versa all 56, 34, 12. Okay, so Faizan, it is clear? If you have any question, you can ask regarding this. Yes, 7, both A and D will be correct. Not only A, both A and D will be correct. Okay, so then I am stopping the session. Thank you for joining. We will again meet next Tuesday, and the link, I guess you will be sent this YouTube link, so don't worry about it. Thank you all.